Hello, everybody. Welcome to MAGFest. You somehow made it to the second panel of the day in this particular room. And we are doing Archiving 101, focusing on digital archiving. My information is available there if you need to reach out to me, but otherwise, I would be happy to take questions at the end. However, before we get going, I should introduce myself, who I am. Hi, I'm Patrick. I am the Digital Collections Archivist at West Virginia University. Yes, they did pay me to say that. I also run the Unofficial Convention Archive as a side project that's not associated with WVU. It's just a hobby that I do. And because I am morally obligated to promote my institution, I'm going to take care of that out of the way now so we don't have to worry about it later. All right, who here has played Fallout 76? I'm sorry. When Todd Howard said, hey, we'll put your campus in a Fallout game, we expected it to be awesome, and then it didn't turn out so much. So yeah, we're a Vault-Tec University, so you have seen the campus there. The gentleman on the upper right-hand corner is standing in front of Woodburn Hall. That is the first building that is at WVU campus, dating back to the 1850s. If you're ever going to see a picture of someone at the university, that is what they're going to be standing in front of. I work at the downtown library. We do, if you're a foamer, we do have the PRT system. Yes, I do take it to and from my job, and it is as awesome as you think it is. And our victory song is indeed Country Roads by John Denver. And you'll hear it frequently every time we win a sporting event. Now, I work specifically at the West Virginia and Regional History Center. We focus in on the history and the people and places in the Appalachia region, as well as West Virginia. I'm showing here some examples of an exhibit that took place last year. We stand with Mothman. Mothman is a really big deal for us. And on the lower right-hand corner, that is what's directly in front of my office. I get to see Don Knotts' gold watch each and every time. So for those who don't know, Don Knotts is arguably the most famous of Morgantown residents has been there. You may be familiar with his work in TV and film, such as Barney Fife and the Andy Griffith Show, the TV repairman at Pleasantville, or Mayor Turkey Lurkey and Chicken Little. Depending on what references you understood about that, tells me a lot about your age. Okay, so enough about that. Obligatory things are done. And I have to give another confession for you. The whole reason that I did this panel in regard for digital archiving was not about digital archiving. It was to reject the claim that has been thrown upon me that I am old. This is lies. This is unfounded. When I asked to cite their sources, they mentioned the Mirror, which is critically not acceptable. So to prove the counterfactual, I have to give some sources of my own in that regard. So here they are. The first ever video game I ever played was Duck Hunt, and by play, I mean watch my dad play, then laugh at the dog every time my dad missed. The first computer operating system I had was Microsoft Windows 3.1 that we got at a trade center back in Fort Washington, Pennsylvania. The first computer I ever bought with my own money was that Sony Vaio machine. I still miss it to that day. I really miss those old days of computing. And I was in my top 25% in typing class in middle school. Yes, flex there. And I also made friends specifically just to go to their house to watch the screensavers on Tech TV. So I think I've established I am not old and in a normal range of human age, so we can move on past that. However, when it comes to computers, getting back on topic, I think of this. This is MS-DOS. This was the glorious days where I put disks at the computer, run in executable files, and play games on the computer at home. However, other people in this room may be younger than me. I know, shocking. And their first exposure to computers could be something like this, a touchscreen device where you can tap and interact with it and get media results. Now, am I saying that I grew up in a better computing time than you? No. This was horrible. in order for me to rebind keys in Quake, I had to learn programming languages in order to trick the computer to throw a grenade and then exchange various guns to then get the gun back out as an offhand grenade. That is horrible. Progress is good. There's nothing wrong about progress. It's an odd thing to clap at, but I appreciate it. All right. However, because of this disparity, we have an interesting divide going on. So this story in particular was the big one that really exposed it out there, but there's multiple stories that are out there that when it comes to computers and technology, everyone has a different baseline to what that is. And that's no fault of your own. It's just your learned experience for that. So that when you come and talk to me about digital archiving, I think you know certain things and you could be oblivious to you. So there's a dilemma to be had here. I could be Principal Skinner and blame the children for not knowing anything about computers. I could be a Ken Burns, push you out of the way, randomly tapping your keyboard and fix the problem for you. Or there's a third way, which I'm going to do, is I'm going to give you a good enough example of this. So if you're watching on YouTube, hi, how's it going? I understand there's going to be some tech people out there. Notice it says good enough. It's not going to be perfect. I am simplifying. I understand that. But please leave your hate comments and subscribe to the MAGFest YouTube channel. It will boost engagement and let people see this there. Also, if you're going to give this the Primogen, make sure you give me the link so I can watch it afterwards. All right. I'm going to go back to the rest of the audience now and continue on with the presentation. All right. So before we begin with computers, we got to go back to the non-computer days and ask a simple question. What is a file? You might have seen it in various forms there, but a file is a device that contains documents that are kept in a certain order. That's it. And now there's other subsequent things associated with the file that may be confusing, so I'm going to demystify it real quick there. So first, we have a bunch of files. We need to put it in something. Where do we put it? We put it in a cabinet. You may be familiar with the option on the far left here. You probably see it at various office supply stores. The middle one is an old school style card catalog that you might see at a local library. Yes, you had to look for books in a card catalog way back in the day. I miss those days. Not old, by you. Not old. But yeah, they get placed in the cabinet. In the cabinet, there contain folders. This is not the manila folder that you're thinking about. These are the hanging types of folders that we put files into. So these are a couple examples of that one. They are not the files themselves. They are simply the vessel of the files. Now, sometimes they would adhere to a file management system. These two options are pretty popular. If you're at my age, to file anything in your home would be something that you may be readily familiar with, or a more recent version would be the Freedom Flyer, which is a combination of labels to put on your the folders, as well as a routine that you set. Like on a certain month, you then exchange documents to go to different locations to make it easier for you to find them in the future itself. So it's not just the organization method, but also the procedures in order to maintain that. And then we come to the actual files. This manila folder is a file folder, and then the whole entity that's being there is what we call the file. There's sometimes an index associated with it. It's like a really long one, and just for ease of reference and ease of finding things there. And in those particular file folders, there are documents. This is the important stuff that you want to have. Usually single page or multiple pages, depending on how it is, and it contains the information you really want to go out of. So, quick recap. We have filing cabinets. In the filing cabinets, we have folders that the files go into. They may or may not be organized by a file management system. And in those folders, we contain the actual files themselves. And in that file itself, there are several documents that are stuff that's important to us that we would like to have there. Good so far? Cool. All right, so now we added computers, making our lives both easier and more difficult at the same time. So let's update some definitions here. So, what is a file in a computer? So a file is a collection of data stored in a container. That's it. I did use a new term, so I need to define that. So what data is any sequence of one or more symbols. That is data. Not really useful data, but it's data. Now, it's easy to confuse it with information, but that's different because that's data organized in a human-readable manner. So that is information. I'm not going to tell you how that works. You can look that up on your own. Now, with these terms, there's a couple revelations that some of you on the internet may be having right now. So let's start with question 1. Blur the definition, is the document a file? Since the document is data that are arranged in a certain order, yes, a document is a file. I think we can all establish that as a baseline. So what about folders in my computer? Are folders a file? Well, they contain data that are arranged in a certain order, so yes, a folder is indeed a file. All right, curveball, what about applications? Applications are data arranged in a certain order, so yes, applications are file. So, big revelation number 1, everything is a file. So whenever you try to correct your old grandmother, like, oh, can you put that file over there? Grandma was right the entire time. So with this revelation, I've been talking about the digital side of things, but I have to give you a shocker. There's this thing that I have to adhere to called physics. And we can't just make things magically out of thin air. They have to come from reality onto itself. So all digital files are physical files. And because of that, there is a tangible, realistic thing that we can control with that. And that is going to be the actual hard drive itself in the computer. Now, your files are good. It's usually represented, if anything, by a series of ones and zeros. Okay, that wasn't big of a revelation. That one, they usually come in 3, so I'll just move on from there. But the hard drive in of itself is going to be the mechanism that your information is. But the ones and zeros do exist, and they are valuable there. So we need to figure out, how do we get those ones and zeros that we may be more accustomed with, and how do we treat it into physical, real world? And the answer, you need to know a little bit about hard drives, so here's a brief synopsis of that.
Imagine an airplane flying 1 millimeter above the ground and circling the Earth once every 25 seconds while counting every blade of grass. Shrink all that down so that it fits in the palm of your hand, and you'd have something equivalent to a modern hard drive, an object that can likely hold more information than your local library. So how does it store so much information in such a small space? At the heart of every hard drive is a stack of high-speed spinning disks with a recording head flying over each surface. Each disk is coated with a film of microscopic, magnetized metal grains. And your data doesn't live there in a form you can recognize. Instead, it is recorded as a magnetic pattern formed by groups of those tiny grains. In each group, also known as a bit, all of the grains have their magnetizations aligned in one of 2 possible states, which correspond to zeros and ones. Data is written onto the disk by converting strings of bits into electrical current fed through an electromagnet. This magnet generates a field strong enough to change the direction of the metal grain's magnetization. Once this information is written onto the disk, the drive uses a magnetic reader to turn it back into a useful form, much like a phonograph needle translates a record's grooves into music. But how can you get so much information out of just zeros and ones? Well, by putting lots of them together. For example, a letter is represented in 1 byte, or 8 bits, and your average photo takes up several megabytes, each of which is 8 million bits.
So now we have the idea. Those ones and zeros are nothing more than magnetic pulses on a spinning hard disk that are read and reread when you ever edit or access a file in and of itself. Pretty nifty. However, to separate it out even further, we actually force a file system to be placed onto there. So it's not optional anymore, we're requiring it. The file system is not the operating system. They work together, but they're not one of its entities. So you can have a different operating system and a different file system. And the file system's responsibility is to locate the files on the hard drive and give it to the operating system to do whatever the operating system is going to do with it. There. So this is the big one, and is basically the most important thing that I have to deal with. So, luckily for you, I brought us a crash course on how file systems work.
Even though the underlying storage medium might
Imagine an airplane.
Even though the underlying storage medium might be a strip of tape, a drum, a disk, or integrated circuits, hardware and software abstractions let us think of storage as a long line of little buckets that store values. In the early days, when computers only performed one computation, like calculating artillery range tables, the entire storage operated like one big file. Data started at the beginning of storage and then filled it up in order as output was produced, up to the storage capacity. However, as computational power and storage capacity improved, it became possible and useful to store more than one file at a time. The simplest option is to store files back to back. This can work, but how does the computer know where files begin and end? Storage devices have no notion of files. They're just a mechanism for storing lots of bits. So for this to work, we need to have a special file that records where other ones are located. This goes by many names, but a good general term is directory file. Most often it's kept right at the front of storage, so we always know where to access it. Location 0. Inside the directory file, the names of all the other files in storage. In our example, they each have a name, followed by a period, and end with what's called a file extension, like BMP or WAV. Those further assist programs in identifying file types. The directory file also stores metadata about these files, like when they were created and last modified, who the owner is, and if they can be read, written, or both. But most importantly, the directory file contains where these files begin in storage and how long they are. If we want to add a file, remove a file, change a file name, or similar, we have to update the information in the directory file. It's like the table of contents in a book. If you make a chapter shorter or move it somewhere else, you have to update the table of contents, otherwise the page numbers won't match. The directory file and the maintenance of it is an example of a very basic file system, the part of an operating system that manages and keeps track of stored files. This particular example is called a flat file system because they're all stored at one level. It's flat. Of course, packing files together back to back is a bit of a problem because if we want to add some data to, let's say, to-do.txt, there's no room to do it without overwriting part of carry.bitmap. So modern file systems do two things. First, they store files in blocks. This leaves a little extra space for changes called slack space. It also means that all file data is aligned to a common size, which simplifies management. In a scheme like this, our directory file needs to keep track of what block each one is stored in. The second thing file systems do is allow files to be broken up into chunks and stored across many blocks. So let's say we open to-do.txt and we add a few more items. Then the file becomes too big to be saved in its one block. We don't want to overwrite the neighbouring one, so instead the file system allocates an unused block, which can accommodate extra data. With a file system scheme like this, the directory file needs to store not just one block per file, but rather a list of blocks per file. In this way, we can have files of variable sizes that can be easily expanded and shrunk, simply by allocating and deallocating blocks. Now let's say we want to delete carry.bitmap. To do that, we can simply remove the entry from the directory file. This, in turn, causes one block to become free. Note that we didn't actually erase the file's data in storage, we just deleted the record of it. At some point, that block will be overwritten with new data, but until then it just sits there. This is one way that computer forensic teams can recover data from computers, even though people think it's been deleted. Crafty. Okay, let's say we add even more items to our to-do list, which causes the file system to allocate yet another block to the file, in this case, recycling the block freed from carry.bitmap. Now our to-do.txt is stored across 3 blocks spaced apart and also out of order. Files getting broken up across storage like this is called fragmentation. It's the inevitable byproduct of files being created, deleted and modified. For many storage technologies, this is bad news. On magnetic tape, reading to-do.txt into memory would require seeking to block 1, then fast forwarding to block 5, and then rewinding to block 3. That's a lot of back and forth. In real-world file systems, large files might be stored across hundreds of blocks, and you don't want to have to wait 5 minutes for your files to open. The answer is defragmentation. That might sound like technobabble, but the process is really simple, and once upon a time it was really fun to watch. The computer copies around data so that files have blocks located together in storage and in the right order. After we've defragged, we can read our to-do file, now located in blocks 1 through 3 in a single quick read pass. So far we've only been talking about flat file systems, where they're all stored in one directory. This worked okay when computers only had a little bit of storage, and you might only have a dozen or so files, but as storage capacity exploded, very quickly it became impractical to store all files together at one level. Just like documents in the real world, it's handy to store related files together in folders. Then we can put connected folders into folders and so on. This is a hierarchical file system, and it's what your computer uses. There are a variety of ways to implement this, but let's stick with the file system example we've been using to convey the main idea. The biggest change is that our directory file needs to be able to point not just to files, but also other directories. To keep track of what's a file and what's a directory, we need some extra metadata. This directory file is the topmost one, known as the root directory. All other files and folders lie beneath this directory along various file paths. We can see inside of our root directory file that we have 3 files and 2 subdirectories, music and photos. If we want to see what's stored in our music directory, we have to go to that block and read the directory file located there. The format is the same as our root directory. In addition to being able to create hierarchies of unlimited depth, this method also allows us to easily move around files. So if we wanted to move theme.wave from our root directory to the music directory, we didn't have to rearrange any blocks of data. We can simply modify the 2 directory files, removing an entry from one and adding it to another. Importantly, the theme.wave file stays in block 5. So that's a quick overview of the key principles of file systems.
So yes, that is file systems in a nutshell. So continuing on, so now let's wrap up everything so we kind of have a baseline. So in this example, I have a file path here. The C drive is going to be the root directory. Usually that's going to be your main hard drive, but you may have different letters associated with different hard drives on your computers. The folder and subfolder here are going to be your directories, so they will be the directory files that you find the file itself. The document, in this case, is the document that you want to open that has the information that you're looking for. And the file extension is usually the 3 letters after the name of the file. That basically simultaneously does a couple things. Number one, it tells the operating system, hey, this file extension wants to be opened up in this program. So the operating system opens up the program. It also tells it, hey, the data in here, you want to rearrange it in a manner and present it in this manner, so that whoever's looking at it can understand what's in the file itself. And with that, congratulations. You now know enough about computer science so that you can understand digital archiving. And we return you back to your regularly scheduled presentation. So what is digital archiving? And that is the practice of saving and maintaining born digital and digitized files for future generations. Now, they're 2 separate entities, but for our purposes, they're kind of the same. It's a file that's on the computer. One you create via opening up in a program and do a file save as. The other one is a physical thing that you scanned into the computer to turn it into a computer file. But for our purposes, I'm going to link them together for this particular discussion. There's also another thing I need to talk about archives with, and it's a big trepidation. Your computer is not a digital archive. I told you they come in 3s. So if you're using a computer and you say, oh, my archive is on my computer that I'm working on, that is not an archive. That is your computer. It has to be something separate onto itself. It is a separate entity that's a different space where you store the information on. And unless you're doing something fancy like virtual machines in order to establish the environment, we're not going to deal with it here. You're going to want to get an external device for it. So we are going to start with the 0 step in this particular process of identifying what files you're going to want to keep, basically separating the trash from the treasure. So you want to keep files that are important to you. It is not everything on your hard drive. The amount of times I get the System32 file from your operating system is countless. Don't do this. I don't need this. This is a waste of space and time. Only focus on the files that have important value to you. So I also don't need your application file. Give me the executable so I can install them on my computer. I don't need all the configuration stuff on your computer. It's fine. So ideally, you want to go ahead and narrow it down. In Windows, you typically use your user directory to help you out with that. So your My Documents folder, your My Music folder, your videos, et cetera, that's where you want to go with the files that you're looking for. Unless you have a special weird file listed elsewhere, then bring that in that way. So you want to pick the things that represent you. Also, you want to make sure that your files are things that you've created. So if you have a Taylor Swift album, I don't want that. Taylor Swift's album's been saved countless times. I got that. If you made a cover of a Taylor Swift song, that is what you want to save because that is unique to you. If there is a special program that in order to open the file or some sort of extension into a program, like a fancy plugin or something, give me that plugin so I can open the file in the future. And if you have other people helping you and they have your files on their computer, you're going to want to get those files onto your computer so you can save it that way. So for group projects like a YouTube video, like you have an editor that does editing and you did the initial run, you want to include that information as well. And the most important question, you need to ask yourself why you're saving this file. Because theoretically, this file is going to be with you for the rest of your life. So if it's something you don't want to be saved, this is the perfect time to get rid of the file to be not into your archive. So just make sure, don't just willy-nilly do it. Just take your time and establish what you're looking for. Once you do that, we finally go to step one. Where are we placing the files? It's simple and straightforward. So you ideally want to put it in a different location, like I said before. And a couple examples are a computer that you store in a closet, some external hard drive, or disks onto itself. And each has its pros and cons associated with it. So hard drive disk, we've already established this. This is the go-to resource. The term for these is spinning rust because they are a mechanical device. They will break over time. So you need to be prepared for that. Now, luckily for you, we have Backblaze to help us out because every quarter they release a report that various nerds will go and read, me being one of them, which hard drive is the best for longevity of storing files. So if it's high on the list, you now know what to buy for your home archival purposes. They also, hard drives, give you between 5 to 7 years worth of valuable lifespan. So you're going to have to save money and recycle hard drives every so often. So when you build up your archive, typically you do it in annual cycles. And you go, okay, this year I'm going to be upgrading these disks. The next year you're going to upgrading those disks and expanding storage to their end. So take some notes down to what it is in order to make sure you keep with that cycle. If you're going to store them in an external location, we have various boxes you can use. This is one that you can buy from an archival store, or if you're crafty and good with cutting foam, you can make this yourself and just get a Pelican case for it. So there are definitely options. Pick whichever one to use if you're going to go down this route. The other types of hard drives are solid state drive. They're typically smaller in size and space, so storage-wise, it takes up less room. They are quicker in accessing files, but you can only write to the drive a limited number of times. It's in the tens of millions, so chances are you're not going to have to worry about it, but I have to mention it just in case. Another option you can do is to create a network attached storage, or a NAS, in order to do it. This is basically a computer with a whole bunch of hard drives that you connect to via an Ethernet cable so that multiple computers can access those particular drives. Typically, here's a couple examples of operating systems you can use it for that particular purpose. Is stripped down. It's usually you connect to it and that's all it does. You can do some fancier things with it, like virtual machines, hosting other software and whatnot. But that's home lab territory. That's not in the scope of this talk. Last, we have good old-fashioned discs. The disc has never died. It just evolved over time. So DVDs, probably the thing you're most familiar with. Goes up to 17 gigabytes worth of storage itself, but however, it can get scratched up if you have scratches on your disk. I would say go to a place that has a professional repair buffing tool. Sometimes you can get it at a game store. Other times you can mail it off to a special place and they will resurface the disk for you. Blu-rays, the good news, they have more storage capacity. You go up to 125 gigabytes. They also have a special coating on them to prevent scratches, which is awesome. So if you see a Blu-ray and it has scratches, do not repair it. You have a bigger problem on your hands. Finally, you have the M-Disc. These are special Blu-ray discs that are purposely treated for archival purposes. That's supposed to last 1,000 years. No one has tested this because of time. So your mileage may vary, but if you really want to be safe, that's an option. 1,000 years, who knows, but maybe a couple hundred, which is still good in my book. If you want to go old school, you can do the tape drive itself. These are actual physical cassette tapes that you have stored data into. This is if you have really, really large files. So the YouTube video there is from Slow-Mo Guys and how they implemented their tape solution. Really fascinating stuff. It is also a gigantic pain in the butt to deal with. So I would advise you to simply go and consult an expert if you desperately need that information. Otherwise, it's not going to be made available there. So this is extreme case. Don't do this unless you really know what you're doing. All right, so now we've established where we're going to put the files. So now we need to fingerprint our data. And now I'm going to define some terms on how to fingerprint the data. So what we want to do is generate a checksum for the values. And what the checksum is you take the bytes that your file consists of, you're going to put a math equation involved with it, and you're going to get a result. That is the checksum. So as an example, you take the bytes, we put it into MD5 or SHA-256. There are more. We don't use them in archiving. If you want to use it, good on you. But for my purposes, those are the big two. And then whatever the value is, that's the checksum that I'm going to save. So as an example, if I had an executable file and I run it through MD5, that result there is going to be the checksum of it. So why do we need to use checksums? So the first reason is if we're downloading or transferring files, this is a good way to check to make sure the file is legitimate. So I generate a checksum, I send the file to you, you make a checksum, we compare results, and if they match, good job. We have a transfer that was successful and you have the information as necessary. Also, it's another option to check for bit rot. So that image there has bit rot in exactly 2 places. So the 1 and 0 got flipped into the opposite value. And because of that, you get distortion here. Now, in this example, because it's just 2 items, it's relatively straightforward to know exactly where to go. But when you have more and more and more options, it gets much more complicated. So a checksum is a great way to verify, wait, that file has a problem, and you can take some steps to remediate that. I'll talk about that a little bit later in this talk. So what do we do with the checksums? We create fixity. So what fixity is, it's a checksum that we deem as important. We basically save this, and in future, we refer to that value as the standard value of what your file should be. Usually you save it into a file that you can open up in anything, an HTML, a CSV, a text file, whatever works for you. And I have to deal with this so much that I've created some scripting code for it. So as you can see here, this is a PowerShell command where if you just copy paste it, it will run, recursively scan all your files, and generate a checksum list for you. Now, I am not going to assume that you all know how to do PowerShell, so I have an easier solution for you. This is a program called Hash My Files. It is a easy thing. You can load it on a USB stick and run it on any computer. There are some modifications you need to do, like dropping columns and whatnot, but once you have everything looks right, you can then export it into an HTML file and have it listed there and show the results there. And you can just use this as a referring to generate your fingerprints or checksums in this case. All right, so we got the disk, we fingerprint it. Now it's time to transfer the files from there to the archive. So we have to define other terms of a copy and a move. They may seem the same, but they're vastly different. A copy is a bit-for-bit recreation of the file itself. But a move is physically moving the file from one directory file to another. So I'm going to use the example that was made earlier in the crash course segment to explain this particular topic. So if we were to move the file, we are simply taking the line out of the directory folder, placing it into the other directory folder, and keeping everything intact. pretty straightforward. When we copy the file, what we do is we go and recreate the file bit for bit. So what happens here is the date created is now changed. So whenever you see the properties of a folder and you go, why is the date modified a older date than the date created? This is the reason why. Most operating systems don't understand the concept and do not save this information. This is what we don't want. Because what we do want is something like this, where we migrate the information over, retain the information, but you still have it on the original source so that if you need to go back and redo it, you have the capability of doing so. And the good news for our purposes is that there are various tools that you can use. I'm going to give you, here's two here. First one, it's called TerraCopy. It's a freeware program. You can buy a license for it for like $20-$30. They give you a little bit of advanced features. You don't need to pay for it. You're just fine with it out of the box, and it will transfer the files and validate that the transfer has been completed successfully. Another one would be rsync, which is a command line interface program. But grsync, it has a special graphical user interface, makes it a little bit easier to navigate it. Does the same thing. Once you configure it once, you can just redo the same configuration and transfer files from one place to another. All right, so we transferred the files off to a different location. Now it's time to back it up. So when we're talking about computers, we are going to talk about saving files as a backup so that we can restore it at a later date. So I'm going to pause the archival discussion for a little bit. We're going to go to computer discussion territory, and we're talking about how to back up your computer. Ideally, you're going to follow the 3-2-1 rule. You want 3 copies of data across 2 mediums, one of which is at a geographically separate location. So, as an example, you can have, say, 1 copy on an external hard drive, 1 copy on a bunch of CDs that you burned, and 1 copy on another external hard drive that you put at your parents' house. This is also or put at a Google Drive, or put at a Dropbox, or what have you. Is there anyone here that does not have a geographically separate location for their backups? All right, everyone that raises their hand, make sure you complete the high five at the end of the talk, and you can talk to each other to solve the problem so you both benefit from that. All right, when it comes to the cloud, this is a code word for someone else's computer. So when someone says, yeah, I back it up to the cloud, are you confident that you want to back it up to someone else's computer? Depending on the answer, depends on where you go in that regard. So, I already did that. So, if you want to keep it secure and make sure that someone else's computer doesn't mess with your stuff, you're going to want to protect the files. So this is where we go into public key encryption. So, this is an asymmetric model where you have the key and it's mixed up so that your key is the only thing that can open it up. So, if the other person's computer want to open up the file for nefarious reasons, they can't do it because they don't have your key. An easy way to generate this is to just generate a key on a key generator. This is an example of an RSA. There's other ones out there. Just pick the one that speaks to you the most. If you want to go even further, you can encrypt the entire disk into itself. Now, this is a little bit advanced territory. There's various options that you can use for it. And also, you want to be very, very sure that you save the keys that you use to encrypt. Because if you lose them, you just lost an entire hard drive worth of data. It's locked and you can't undo it. Additionally, you need to have a plan for when inevitably everyone leaves the mortal coil. So you need to add a will and testament and explain, when I die, this is where my passwords go to. This is an escrow box with my keys that are secure, that's only opened at this particular time. This involves a lot of third parties. This is where you have to go into like lawyer territory, consult a lawyer. I'm just telling you, this is something that you have to do if you want to go really serious with it. And the book Death Glitch is a great example of some examples of how it plays out in real life. This is where also fixity comes in, and super nice. We can use fixity combined with a backup in order to ensure that we can restore any damaged files onto itself. So ideally with the 3 copies is good. If you have more, that's better. But I'm going to show you the 3 copy example and how it's going to work. So here's the example. Say you got a file, and we are going to go through the fixity process. So we run it through the algorithm or MD5, and we generate the fingerprint or the checksum of the file. Then we take that value and we save it to the fixity file for our future purposes. there. So as long as they match, we know we're good. Time advances. You go various civilizations came and fall, and we are trying to access your files in the far future. So we do the same thing. We take the file, we run it through the algorithm, we get the fingerprint, but however, we realize the problem. It does not match the checksum. Something is suspicious here. Now, it could be a situation where our fixity could be incorrect, and that's a correct file, but the good way to find out is going back to our backups. So, go to backup, we locate the file, we do the same thing all over again, and we realize it's a match. So we now know that past dust and present dust have a match in two different locations. But that third file could still be the original file because there's a possibility that both the backup and our original copy were messed up. So how do we determine that? We got bust out the secondary backup. Do the same thing. It matches. Everything matches. So now we know that that file is in question. So you remove that file. You replace it with a copy or for your backup or secondary backup. Place it back in the original spot. You have your files restored and have full confidence that you have the information saved. All right, now we're going to go out of the computer talk and go into the archival talk. So, backups are not your archives, but archives have backups. So wherever files you transfer off to your archive, you're going to have to back up the archive in the same way. So archival, think of it long-term for the far future, and your backups is your readily local copy if you need to restore it there. So what does this look like? So I'm going to give you an example following the 3-2-1 rule that I explained before and give you the ideal scenario with infinite money and resources situation. You have a computer. You have a backup location for it. Every week or so, you run a script in order to back up the files there. There's some tricks you can do to save some space, but you just do a backup. You have a secondary backup location. And every so month, you sync your backup location to your secondary backup location so that they're in sync with one another and that they're there. And then you have some place in the cloud or some other parent's house. And then every so often, you transfer that stuff over to them on a routine basis, usually quarterly, but you can do it more frequently if you want. So all that is just backups, nothing to do with archiving. Let's add archiving to the equation. So we review the folders, or the files and folders, onto the secondary backup, and we determine what is going to be considered your archival file, and separate those out. From there, you have a very old computer that's not very useful. That's your archive, and we're going to take that and batch them up together and do it all at once. So sometimes people like to do this on like every 6 months or every other year, but that's effectively, once you do it, you just do it all at once and transfer it there. Then you have a secondary backup of your archive, and you sync it together over some period of time. In this case, I have it bi-monthly. Then you also have the remote storage, and then have a backup reserve of your archive there. This is very expensive. Most humans are not going to do this. I am not going to tell you this is what you're going to do right away. However, if you can build it out piece by piece, that is ideal. But that is effectively how you should properly back up and archive your things, and why I will always have a job in my field. All right, so we got everything transferred. We got everything backed up. We're good to go, right? Nope. We need to add metadata. Because while you know what's in your files, I don't know what's in your files, and I would really like to know what's in your files. So adding metadata to the files itself is going to be valuable there. So let's start. There's two types of metadata. First, there's technical metadata. The good news, you don't need to worry about it, because chances are it's already built into the file itself. This is an example of a photo using EXIF that was shot on an iPhone. You'll occasionally see a YouTube video, oh, do this to remove the metadata from your images. Don't do that, please. There's valuable information that I'm going to use to figure out information about your image. Like, where did you take the picture? That is useful information that the technical metadata is going to take care of. So that's that. What we are concerned with is descriptive metadata. This is how we describe what the file is to someone. And there is a multitude of options you can choose in order to determine what to use. I'm going to go with the simplest one, which is Dublin Core. Why is it simple? Everything you can describe into an image is those terms. That's it. And I'll give you a quick rundown. So, title, what's the name of it? Subject are the keywords that you will use in a search in order to do that. So, anytime you use a hashtag on social media, that's the subject. Description, you basically describe what it is so that future people can know what it is. What type is it? Is it an image? Is it a video? Simple, straightforward. A source is where if derived from a different thing. So this is a paragraph of a larger book. You would cite the source of the book where it came from. Very straightforward. If you like to use fancier terms, this is my homepage that I use on my job. It has everything under the sun for American archival purposes. Basically, you type in the value, it will give you the controlled vocabulary version of it, and just copy and paste that, so you don't have to reinvent the wheel. Coverage is anything associated with it, so any time and place or moment in regard to that, it can be added there. The date, very important. There are different types: date created, date modified, the date that you exported, the date you published it, all the dates. I want that. What language is it in? We're in an English-speaking country, so it's English, but if you're bilingual, if you have something in Spanish, you want to designate that. Creator, most likely you, maybe someone else, but you want to include that there. The publisher, if you have it published out to like YouTube or to a journal, you put it there. Chances are you're going to keep it blank. A contributor is another person that helps you in the creation of the object itself. So if I were to create this PowerPoint and I gave it to my coworker to edit it, my coworker would be a contributor as the editor for this particular file. Last one's real quick. What's the licensing associated with it? Because of very dumb decisions back in the 70s, we are forced to have everything under copyright. So you need to specify what copyright things are in order for people to access them. Go to Creative Commons, take the quiz, and it'll tell you the answer that you're looking for. The format is basically both on a file identity level as well as the dimensions of it, usually size in pixels as well as the extension type. Identifier, if you're going to have like an ID number as a quick reference to it, that's where you put it. And finally, if the file is related to something else, this is where you put it under relation. Usually an is statement like, this is part of something else, or this is processed by da-da-da. It's those particular types. So I gave a whole bunch of stuff. So here's an example of this exact presentation in this particular format. Now here, what I did was I just opened up Excel, typed everything in there, and placed it there. And as you can see, you don't need to fill out everything if there's nothing to be there, hence why I have NA there, but you can leave it blank. It's fine. But effectively, you get the idea of how to format that. Now, if we're talking like real world, like stuff I do with my job type of things, I don't use Excel. I use stuff like XML here. So in this image itself, there's a bunch of text there in XML format, but it's effectively the same thing. It's just coded in a slightly different manner. Makes it easier for computers to read it and interpret it and be indexable on there. So if you're a little bit tech savvy, this is the way you want to go. If not, just use the format example and you're going to be fine. Lastly, you want to find something that's going to work for you. So if you don't want to do Dublin Core, that's okay. If you want to make something up, sure, I may bang my head against the wall slightly for that. But at least if you have figured out whatever works for you, do it. And write down and explain how it works so that I, not being you, can understand your method of madness and so that I can understand what's in your files. All right, next, we're going to normalize the file. So we have the metadata, we can transfer it over, and normalization is the process of making sure that we can open our files in the future. Because this might not be present to you now, but in the past, if there's companies that made various versions of like a word processing software that are no longer in business. And because of that, when you try to open it, you can't install the program on your computer, so you can't open it. So normalization converts it into a different format so I can open it up on someone else's computer. Here's an example of the de facto standards in archival terms of file formats. So if you have anything that's not in this format, go ahead and put it in this format. There's various tools and tips out there that you can use to help you with this particular process, whether it be scripting, some programming, or some third-party tools that will help you with that. Yeah, an easy way, just open up the file save as, save it as that particular file type. You're good. Otherwise, you want to do the scripting procedures, and you'll get the information there. Once you have that, you now have two copies of the file. So you have an original copy, and you have an access copy. The normalization file is going to be the access copy. This is what people are going to use to open up the file on their computer. So we want to make sure we organize it in a way where the access copy is separated from the original copy, but you can go back to the original copy if you really need to do that. This is the majority of my day of my job. I'm going to give you two approaches on how to do this. One way is to basically put them in a same folder structure. Another way is to separate it out into two separate buckets and then present the information there. It does not matter which way you choose. As long as you choose a method of doing it, you're going to be okay. All right, now I take a look at my watch and look at the time and go, ooh, I get to show you a meme. Yes, digital archiving has a meme. And this one in particular is an old series that came out over a decade or so ago. And it's going to summarize a lot of what we just talked about. And you can all have a good laugh at some stuff that I've worked with in the past. So I'm going to load it up and enjoy. Un momento. Da, 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 da. That works. All right, so I was going to show you a meme. So that is Digiman. If you want to look it up, it's under We Preserve YouTube channel. They are all hilarious. However, I'll just do the wrap up in the old style. So the steps that you're going to want to do to digitally archive your items. You want to identify what you're going to want to keep, separate stuff you don't want to save, and only carry about the stuff that you want. Secondarily, you're going to find a place to put it, whether it be an external hard drive, some disk, or whatever storage value. You want to capture the fixity of the files that you can use to refer to that into the future. You're going to transfer the file over from one place to another using the tools I mentioned before or some other tools that you may locate there. You're going to create a backup of everything so that if it gets damaged, you can restore it from that particular backup. You're going to add metadata so that in future generations, they understand what the file is and why it's important to you. And then you're going to normalize the files to make sure that those files are able to be opened up on computers with various technologies that are coming in the future that are not there. So, with that, my time is up for now. And if anyone has any questions, feel free to ask. But otherwise, thank you for coming out. Enjoy the rest of your MAGFest day.